Welcome back. In this example, we're going to look at the concept of percent ionization. And so percent ionization is another way to look at or to indicate the extent at which a reaction goes to products. And so we use this often when we talk about acids to see, how much of the acid has been converted into the ion, the either hydronium ion for an acid, in this case, or hydroxide ion if we were talking about a base. So we're looking at the percent of reaction. Now, to remind ourselves, the equation for percent ionization is the percent ionization equals the concentration of hydronium. So that's, in the book that might say that might be ionized acid, but we can think about that as the percent of hydronium, and this is of course at equilibrium, divided by the concentration of our acid at the beginning. So our HA, what we can call the initial concentration or the starting concentration, times 100 to put it in terms of a percent. So that's the equation that we're interested in. Now in this particular problem, we're trying to find the percent ionization of a 0.25 molar acetic acid solution, this H2CO2. So of course, one thing that we're going to eventually need is the Ka. So we'll go ahead and we will look up the Ka of acetic acid, and we would find 1.8 times 10 to the negative fifth. Now, we're going to write out our acetic acid equilibrium. So HC2H3O2, and I'm just going to dispense with the aqueous. We should know now that it's aqueous, and we should write it properly, but just to make it a little bit quicker here, I'm not going to write the aqueous. We're going to note that the water is, of course, in the liquid phase, and this is in equilibrium with our conjugate base, the acetate ion, plus, of course, hydronium ion. Now, if we think about what we need to solve for the percent ionization, we need two values, right? We need the initial acid concentration, which we have from the problem. We also need the equilibrium hydronium ion concentration. Now, this is what we have to solve. Now, if they gave us the pH, we could solve it from the pH. But in the absence of a pH value, we're going to have to go through and solve our Ka expression to get there. Because remember, the Ka for this, right, is going to be the concentration of C2H3O2 minus times concentration of hydronium ion over the concentration of acetic acid. And so we have this value right here. This is what we're trying to get. So we're going to set up our Rice table here. We're going to have our acetic acid. We're going to have our acetate ion. And we're going to have our hydronium ion. We know initially this is 0.250. We know this is 0. And this is approximately 0 at the beginning. We can quote our changes in terms of x, so we don't know anything about equilibrium. So we know this is going to go down by x, up by x, up by x. And our equilibrium concentrations can be found with 0.25 minus x, x, and x. So now we can go ahead and use our Ka expression. Is going to equal x times x over 0.25 minus x. Now, as I mentioned before, if you look at the values, we're at least 3 orders of magnitude apart. So, as I said with a lot of these, we're going to use the x is smallest approximation to simplify here. So we can say 1.8 times 10 to the negative fifth equals x squared over 0.25. Now the math becomes pretty straightforward. And so we can solve down and get, x squared equals 4.5 times 10 to the negative sixth. X then equals 2.12 times 10 to the negative 3. So we have our x value. We're going to then plug this in to solve for our hydronium ion concentration. So that's just simply equal to x. So we have our hydronium ion concentration. Now we can sort of circle back and solve for our percent ionization. Going to equal our 2.12 times 10 to the negative third divided by 0.25 times 100, and what we'll see is that our percent ionization equals 0.849% ionized. Which is our target answer here. Now, you might be noticing that I didn't check to see if the approximation was valid. But one thing I'll point out is, calculating the percent ionization, notice that it's the same calculation we do to check the approximation, right? It is our x value, because hydronium is simply equal to x, divided by our initial concentration times 100. So, if we were to check the approximation, we'd be doing the same calculation, and clearly this is well under 5%. So, when we check our approximation in these weak acid problems, we are almost always calculating the percent ionization. Because you'll notice in all these problems we've done so far, the hydronium concentration is simply equal to X. Okay? So that's something to sort of remember when you're working through these problems. All right, so that's a percent ionization. So we're going to continue on with doing some more problems, and these will be posted in the appropriate sections. But I'm going to turn our attention to doing some problems looking at bases now.